Hello Physics 341 and welcome back to another video answer key. Today we're looking at problems dealing with refraction and Snell's law. So our first problem is simply to define refraction, and that is the bending or the changing of light's path as light passes between two different materials. And I apologize that I'm left-handed. So light goes from one material to another. So for example, if I have air and water, that light comes in at some angle and then it bends to a different angle as it enters the water. So light changes its course based on what material it starts and ends in. What does refraction depend on? Well, we have a special formula known as Snell's law that says N1 sine theta 1 equals N2 sine theta 2. And what we're looking at is the properties of the first material it starts in on the left and the material it ends up in on the right. So what we have is these N's are called the indices of refraction. And this kind of tells us roughly, it's not the same thing as density, but denser materials tend to have larger indexes of refraction. So air has a smaller N than water might on the other side. This first angle here is the incident angle. And the amount of refraction is this second angle here, the refracted angle, how much it actually bends to. So if we rearrange this equation for sine theta 2, we get that N1 over N2 times theta, or sine of theta 1, is equal to each other. So the amount of refraction depends on sort of the ratio of the starting index of refraction and the final index of refraction and the angle that the initial material came in at. So it depends on the indices of refraction, and it depends on the incident angle. So we might ask, the wave has, three special properties to it. It has the speed, the frequency, and the wavelength as a wave passes from one medium to another. It's really going to depend on whether it goes from a high to a low index of refraction. So let's look at both of these cases. So we have low to high. This would be like our air to water we drew above. We're going to see the speed is going to go down. When you go into a denser material, your speed's going to get slower. Your frequency actually stays the same. And this is going to be true no matter what. That's kind of the defining thing that has to be constant about a wave entering materials, is that it has to have the same frequency. So the amount that wave is changing, oscillating up and down, is going to be the same no matter whether it's in air, vacuum, water, glass, or whatever. So the frequency is always going to be the same. The way you think about that is if you're standing at the edge of a pool out in the air and you jump up and down 3 times, you've jumped up and down 3 times. If you went into the water and you have half of your body out in the air and the lower part of your body in the water, if you jump up and down 3 times, both halves of you still moved up and down 3 times. And so the wave is behaving the same way whether it enters any kind of material. So whatever jiggles in the second material has to jiggle the same in the first material. Your wavelength, if frequency stays the same, the wavelength also has to decrease. And that's because velocity equals F times lambda. If the wavelength goes down and the frequency is the same, the velocity has to go down to balance that out. The opposite's true if we go from high to low. When we go to a less dense material, the wave is sort of freer to move, and therefore it's going to be able to move faster. F is still the same, and lambda is also going to increase as I go from a high index of refraction to a lower one. So if you go into a denser material, a stickier material, you're going to slow down. If you end up freer, you're going to end up going faster in the end. All right, so we have this idea of total internal reflection where all of the light that exits a material ends up getting trapped. So here our light comes in and it's going to bend away from the normal so much that it actually ends up trapped back in the material or reflecting back. Light will only bend away from the normal if it enters a lower index of refraction. So for this to happen, we have to have low N and a higher N. So we only get total internal reflection, or as I'm going to call it TIR from now on, if N1 is greater than N2. If it's the other way around, you're not going to get this to happen. You also have to be larger than or equal to a special critical angle, which we'll solve for in just a moment here. So total internal reflection happens only if you go from a higher index of refraction to a lower one. All right, let's actually work out some problems. So our first problem here, we have a light ray with angle of incidence 41 degrees moves from quartz, N equals 1.54, to ethanol, N equals 1.36. Now, part A asks you to draw a picture, but really for these kinds of problems, you should always be drawing a picture whether or not you're asked to or not. So let's just draw that picture as part of our calculation of part B. Calculate the angle of refraction. So here's our picture. We have our surfaces. The top represents quartz, and we can signify that with N equals 1.54. And the bottom is our ethanol, which has N equals 1.36. We always draw a normal line perpendicular to the interface so that we have a way to reference our angles. And our light is going to come in at an angle of 41 degrees. And we want to know what angle we end up, refracting at. What is the angle of refraction? So we want to solve for this theta 2. We're going to use Snell's law. We have N1 sine theta 1 equal N2 sine theta 2, and we're going to solve for theta 2. So I'm going to divide both sides of my equation by N2 to get theta 2 all by itself, or sine theta 2 anyway, divided by N2 equals sine theta 2. Now I can start plugging in my numbers. I'm going to get 1.54 divided by 1.36 times the sine of 41 degrees. Make sure that your calculator is in degrees mode, otherwise you're going to have a bad day. And that's equal to sine theta 2. I plug all these numbers into my calculator. I'm going to get sine theta 2 is equal to 0.743. And I'm going to do the inverse sine of both sides. So I finally end up with a value of almost exactly 48 degrees. So that is our refracted angle. It makes sense that 48 is larger than 41 because we're going to a lower index of refraction material. That's our ethanol here, and our light is going to bend away from the normal to make a bigger angle. So this checks out. We're also asked to calculate the critical angle. So the critical angle happens when the light bends so much we end up back in the material, and this happens at minimum when our angle theta 2 is equal to 90 degrees. So if we draw a picture again, we have our light coming in at some critical angle we want to find, and then the light's going to bend so much it doesn't actually exit and moves along the lower boundary of the interface here. This works, again, because ethanol has a lower index of refraction from quartz. If it was the other way around, this question wouldn't even make sense. So we can plug in the numbers that we know. We're going to solve theta 1 is now the critical angle, theta c. Divide both sides by N1. We get sine 90 is 1, so we're just left with 1.36 on the other side, divided by 1.54. And now I'm going to do inverse sine of both sides to get theta c equals sine inverse of 1.36 over 1.54, and this ends up being 62 degrees. So if the light enters this interface at 62 degrees or larger, none of the light will exit and will all be trapped inside the quartz crystals. All right, moving on. Now we've got a ray of light has an angle of incidence of 30 degrees on a block of unknown material and refracts at 20 degrees. We want to know the index of refraction of this material. So we've got light. It doesn't specify where it's coming from, but usually you can specify that we have air here, which has a simple index of refraction of about 1. Over here, we have a mystery index of refraction that we don't know, and that's what we're trying to solve for here. So in the previous problem, we looked for the angle. Here we know both of the angles, 30 degrees and 20 degrees. And we want to figure out what index of refraction makes this relationship between the angles. So we're going to set up our equation the same way. N1 sine theta 1 equals N2 sine theta 2. We can plug in our numbers. We have N1 is just 1. Sine theta 1 is sine 30 equals N2 sine 20 degrees. So N2 is just sine 30 degrees over sine 20 degrees. We put that into the calculator and we get that N2 is 1.46. It's important to remember that the index of refraction actually has no unit, so this is the one safe time to leave them off. So here I'm going to write 1.46 with nothing else after it, and that is my N value. It makes sense that 1.46 is greater than 1 because the light bent toward the normal here, and that only happens when you go from a lighter to a denser material. Our final problem on this worksheet, we have this sort of long story here. When light enters a certain liquid from water, it bends toward the normal. When light enters that same liquid from crown glass, it's a special kind of glass, it bends away from the normal. So we can draw pictures to help us figure this out. We're entering from water, so we start in H2O and we end up in our mystery liquid. So this one says it bends toward the normal. The light comes in and it goes toward the normal. When we have glass as our starting material, we still end up in our mystery liquid. But this time it says the light bends away, so it gets further away from our reference point. So we have a larger angle here than we had over here. What does this tell us? What can we conclude? Well, we can conclude that N of the liquid has to be greater than N for H2O. And we can conclude that it has to be less than the N for glass. Yep, I did that wrong. Less than the N for glass. So in other words, it bends towards the normal when it goes into the mystery liquid from water because that denser material bends it closer to the normal. And that means that it must be less dense than glass because when we go from glass to the liquid, it goes the other way. So our conclusion is that the index of refraction of this liquid has to be somewhere between that of glass and water. It's smack in the middle of those two materials. So in summary, low to high N, we bend toward the normal. If we go high to low N, we bend away from the normal. The light is free because it's no longer oppressed in the lower N. All right, that does it for this worksheet. Hope you found this helpful. Again, if you have any further questions, please contact either me or Ms. Jenkins, and we'll be happy to help you. All right, good luck, and thank you.